Hello students, welcome back to the next module of our chapter called electrostatics. Now students, in this particular module, we'll be deriving an expression of electric field intensity due to charge cylinder of infinite length, right? And deriving this particular expression by using Gauss theorem, right? So that's why it is referred as application 2 of Gauss theorem. Now students, in the first application, we have derived an expression of electric field intensity due to a charge sphere, right? And using that concept of Gauss theorem again, we'll be finding out intensity due to charge cylinder, right? Now before starting with the discussion of this particular module, let us first discuss the flow of this particular application. Now students, here we are supposed to find electric field intensity due to charge cylinder, right? So our first point of discussion would be cylinder, right? And since the cylinder is charged, certain amount of charge would have been given to this particular cylinder, and this charge will get distributed on the surface of cylinder. So next point of discussion would be charge and its distribution, right? Now students, whenever we are supposed to find electric field intensity, we always find that intensity at a particular point. So our next point of discussion would be point P, where we are supposed to find electric field intensity. Now students, again over here we are supposed to use Gauss theorem, and while using Gauss theorem, we are supposed to create a Gaussian surface, or we are supposed to imagine a Gaussian surface which will enclose the charge. So our next point of discussion would be Gaussian surface and the enclosed charge, right? Now once we are done with the discussion of all these points, then we'll calculate T and EI, that is total normal electric induction, and we'll be calculating T and EI by two different ways. Firstly, we'll be calculating T and EI by Gauss theorem. And according to Gauss theorem, T and EI is equal to enclosed charge, and we'll call that as equation number 1. Secondly, we'll be calculating T and EI by general method or by mathematical method. Now we know formula for T and EI. What is the formula? Formula is integration over a closed surface epsilon E cos theta ds, right? Then after this, we'll be discussing on E and theta. What is E? E is electric field intensity, and theta is angle between vector E and vector ds. Now after this, we'll integrate, and after integrating, we'll get the value of T and EI, and we'll call that as equation number 2, right? Now students, once we are done with the discussion of T and EI, we'll equate equation 1 and equation 2 to get the value of capital E, that is electric field intensity due to charge cylinder of infinite length, right? Now let us move further. Let us start with the discussion. Now first of all, we'll discuss about cylinder, charge and its distribution. So let us consider an isolated cylindrical conductor of radius capital R and infinite length, right? So let's say we are having a cylinder, rather we are considering a section of cylinder which is infinite, and this particular cylinder is having radius equal to capital R, right? Now to this particular cylinder, charge would be provided, right? So let's say charge which is provided to the cylinder is lambda per unit length, or I can say it is carrying a charge lambda per unit length. Now since this cylinder is conductor, so this particular charge will get uniformly distributed on the surface of the cylindrical conductor. Now see this, the charge is uniformly distributed. Now since it is uniform distribution, I can say linear charge density lambda, it is given by charge capital Q upon length capital L, right? Where Q is the charge on the section that will get enclosed, and L is the length of the section that will get enclosed, right? So let's move further. So I can write lambda, it is equal to capital Q upon capital L, right? So this is nothing but the formula for linear charge density, and this last expression is very important. Kindly note it down, right? Now let us move further. Now students, while discussing intensity, we are supposed to find intensity at a particular point. So now next point of discussion is point P. So let us consider a point P over here, right? And this point P is at a distance of small r from the axis of the cylinder, right? Now see small r and capital R. Which one is greater? Yes, small r is greater than capital R. And if small r is greater than capital R, I can say this particular point P lies outside the cylinder, right? Let's say if small r was equal to capital R, then this point P lies on the surface of the cylinder. And let's say if small r is less than capital R, then this particular point P lies inside the cylinder. So based on the values of small r and capital R, we can find out where point P is present, right? And in this particular case, small r is greater than capital R. That's why I can say point P is lying outside the cylinder, right? Now we'll be enclosing some section of the cylinder, right? Or rather we'll be making Gaussian surface and will enclose some charge. So let us consider an imaginary cylinder of radius equal to small r, and let's say length of this particular cylinder is capital L. So let's say here we are having a cylinder which is having radius equal to small r and length is capital L. And since this particular cylinder is enclosing some charge, it is referred as a Gaussian cylinder, right? Now let us move further and let us find out the enclosed charge. Now student, from the formula of lambda, we can get the value of capital Q, right? So therefore I can write capital Q, which is enclosed charge, it is equal to lambda L, right? Where capital Q represents the enclosed charge, lambda is the linear charge density, and L is the length of the Gaussian cylinder, right? As the length of Gaussian cylinder increases, the enclosed charge will also increase. So students, in this particular module, we have discussed till Gaussian surface and the enclosed charge, and the mathematical part we'll be discussing in the next module. Till then, keep learning. Thank you.